Okay. It's my pleasure to introduce Francesca DeMeo, who's our speaker today. She did her PhD at MIT, having grown up in Boston. Then did her one sojourn away from Boston when she did her PhD at the Observatoire in Paris. Then she went back to MIT to do a postdoc, and then to Harvard as a Hubble Fellow, and is the only person I know of who's given up a Hubble Fellow to start up a company, which she does more or less full-time, as well as doing a very active research group. So if anyone's on Amazon and needs some clothing, please go to her company there.
Also a famous business.
Yes, of course. So anyway, today she's not going to be advertising her company, but she's going to be talking about asteroids as records of solar system history.
Thanks so much, Cal. Excited to be here today. Thanks for having me, everyone. So I'm going to talk to you today about asteroids and how they can tell us about solar system history. So I'd like to start off with some general information about asteroids and about solar system science, since I know all of you come from different backgrounds, whether it be from really close up looking at meteorites or really far away in astronomy and astrophysics. So asteroids have a lot of really interesting reasons to study them. A lot of them have to do with the Earth and the inner solar system, because asteroids are building blocks of the terrestrial planets. They contain organic matter that could help explain the existence of life. They're potential sources of Earth's water. They're also important for things like planetary defense and can be resources for humans in terms of their water and rare earth elements for space exploration. And also from a more astronomical sense, they're related to debris disks around older stars. So we can look at the debris around older stars and compare them to what we see in our own solar system. But the main reason that I study asteroids, and what I'm going to talk about today in my talk, is how asteroids are related to understanding the formation and evolution of our solar system. Asteroids contain a record of the conditions of the protosolar disk. They can tell you about the timing of planetesimal formation and then the temperature and compositional gradient across the solar system as they formed in all different locations throughout the disk. And they can also tell you about the evolution of the solar system, because even though physically and compositionally they preserve a record of where the initial conditions in which they formed, their current locations tell you about different movements, migration periods that have moved material and displaced material throughout the solar system. To give you just a little background on where in the solar system we're looking, so here you have the sun all the way out to the Kuiper Belt and Oort Cloud and beyond. So this is Scott Shepherd's land out here, and I'm just talking about this little spot close to the sun where the main asteroid belt exists between Mars and Jupiter. So it's a really narrow location, very close to the sun and very warm. This is what an asteroid looks like when I observe it through a telescope. I like to show it just because from the astronomer's perspective, usually what they're looking at doesn't move. And so you can see these near-Earth asteroids will stream across the sky at a really rapid pace. We've observed some that have moved as fast as 60 arc seconds a second. You need to get a special telescope that can slew that fast. But generally, they only move a fraction of an arc second a second.
Is north up there?
Yes.
That asteroid's moving almost due north.
Yeah. Yeah. And this is what asteroids look like up close if you look at them from a space mission flyby. This is Lutetia, Mathilde, so all different asteroids, all different shapes. They range in size from Ceres, which is 1,000 kilometers across, to really small. Most of the ones we observe at the smallest sizes in the main belt are about 1 kilometer across. And then, of course, in the near-Earth object population, we can see things as small as tens of meters across. So the things that I want to talk about today include the compositional diversity of asteroids, the compositional gradient of asteroids, so how they're positioned as a function of distance from the sun, and if we see any trends. And then after I present sort of a compositional map of where asteroids exist in the main belt and what that means, I'll go into some sort of sub-questions related to that map that have been follow-up work, essentially looking at the details of where all the asteroids exist and what types they are and what questions they can answer about the formation and evolution of asteroids and the solar system. And so specifically, one of the topics that I'm talking about is going to be the distribution of differentiated material, because that's something that I've been doing some follow-up work on. So here's a plot of chemical condensation. So when well, now and also at the beginning of the formation of the solar system, there was obviously a temperature gradient across the disk in terms of function of distance from the sun. So when you're closer to the sun at higher temperatures, you have metals condensing. As you move further away, you'll get things like silicates and carbon-rich silicates, and of course, if you move far enough away, you get ices condensing. And so if the asteroids formed locally here between Mars and Jupiter, you would think you'd be able to recover the compositional gradient from the initial conditions of the disk. So things that formed closer to the sun would have a warmer looking composition, materials that formed in a warmer environment, and further away you'd have materials that formed in a colder environment, so more carbon and ice rich.
Except that things migrate around, that's a problem.
Since the formation, yes, exactly. And so you're untangling the history of the composition versus where they are today and where you expect them to have formed. So how do you tell the compositions of asteroids? Well, you'll have to look at them from near IR spectroscopy, visible and near infrared spectroscopy, and you basically look at the difference between the solar light and the light that's reflected off of the surface. And any differences, so any absorptions, for example, will tell you about minerals that exist on their surfaces. There are 24 classes in this taxonomy, and of course there's other ways, so spectra, albedos, and densities can give us the best clues to asteroid compositions, but this is just a spectral taxonomy. There's a lot of different classes, but two of the most important groups to know about are the S-type asteroids and the C-type asteroids, and those make up probably at least 90% of the asteroids that we know of in the main belt. S stands for either stony or silicaceous. They tend to be more like ordinary chondrite meteorites, and the C-types stand for carbonaceous, tend to be more similar to carbonaceous chondrite meteorites. So S and C are the main ones, the most abundant classes. I'll try not to get into too much of an alphabet soup when I go through everything. And so the key really to understanding composition is not just to divide all the asteroids into different classes, but to relate those to the meteorites and the minerals that are on the surfaces of these asteroids. So you'll take the spectra of the minerals or meteorites, compare them with the asteroids, and figure out what the compositional match is. Unfortunately, we can't actually put the asteroids themselves in a lab and measure their exact compositions, so we take the meteorites that have fallen from the sky and do that and get a lot more detail from there. But of course, then you're playing a linking game between what you see from a point source in space to what you have in your lab. And so here's an example of what we'll do. You can look at pyroxene. It has a really clear, so this is near-infrared spectral reflectance. You'll see at 1 micron and 2 microns, you have very clear, deep absorption features. So that's very characteristic of pyroxene. You can look at a V-type asteroid, which is a nearly perfect match. And that actually matches the surface of Vesta, one of the largest asteroids in the main belt, and also one of the targets of the Dawn mission. And so it sort of seems simple. You can match it up. The absorption bands match. Of course, there's a lot more detail you can look into the depths and the positions of the bands. You can do the same thing with olivine. Olivine has a really clear, deep 1 micron absorption feature. It looks somewhat similar to an A-type asteroid that also has a deep feature, although is much, much redder. And asteroid Aspirina is one example of an A-type. And so it seems simple. You can match the mineral spectrum to the asteroid spectrum and have a sense of what the dominant composition is, at least in terms of what you can observe spectrally. But then one of the problems is once you add a few percent carbon, here's a spectrum of carbon right here. It's only got an albedo of a few percent. And so once you add a few percent carbon, you essentially mask any other features. It dampens the spectrum, lowers the albedo, and masks the features. So essentially there could be anything on the surface, and really all you're detecting is the carbon. So it's not as simple as it seems. It would be nice if we could just have a simple match like this with all the asteroid types, but we find it's actually a little bit more difficult to understand the compositions of everything. One caveat I like to give is the complexity of asteroids is when you're looking at it at different scales, we tend to think differently. So as an asteroid scientist, I kind of think of an asteroid as a spherical blob. Everything's kind of homogeneous over the surface, but of course if you look at it up close and look at all the details, there's an enormous amount of information that you can get even at the micron level, the micron scale, that we just tend to not think about when we study asteroids as a whole, just because when you're observing something spherically averaged as a point source from the ground, you just obviously can't get that level of detail. So this is where the asteroids are located in the main belt. So they're between about 2 and 3.5 AU. So this is Mars here at 1.5, Jupiter at 5.2. And the asteroid belt is carved into different regions. This is the main belt here. There's the Hungarians that starts beforehand. The main belt is carved into the inner, mid, and outer belt. And you can actually see physical lines separating them. This is the resonances. Most of these are resonances with Jupiter that are actually unstable for orbits. So you can see that over time, we've lost any bodies that have populated these regions. There's also the Cybele, Hildes, and the Jupiter Trojans. These are in resonances with Jupiter, which stable resonances as opposed to unstable resonances. So that's why you see these concentrations just in these specific regions. These are the near-Earth asteroids that have orbits that cross or come close to the orbit of Earth. I don't focus on that much in this talk, but I guess it's interesting to see that they're there. This is a density map, so you can see yellow is the most densely populated by number, and blue or purple is least densely populated. So you can see a bigger concentration here, not quite as concentrated here. A lot of that's just observational bias. As you get closer to the Earth and closer to the Sun, things are brighter and easier to detect, so that's why we find more closer in than further out. So the next thing I want to talk about is how asteroids are distributed throughout the main belt in terms of composition. So you could take this plot here of where all the asteroids are located, and this is orbit, so you're looking at distance and orbital inclination. And then you can look at the spectral taxonomy and look at what the trends are over distance, so over 2 to 5 AU from the Sun. And so this work here is actually from 1982. It was one of the first major works looking at compositional maps of the asteroid belt. And it was made using the 1,000 largest asteroids and taking spectra of each one. And so what they found, this was a really interesting result, is they'd find peaks or groupings of different classes of asteroids as a function of distance from the Sun. And even more interesting was not that they were clustered locally, but that they seemed to have a clear gradient with what the temperature would be expected in each region. So E and S were expected to form in a warmer environment, whereas C, more carbon rich, was a little bit further out, and then P and D, these tend to be more organic rich, expected to form even further away than the C types. And so at the time we thought, wow, well, we've solved the puzzle. This is the compositional gradient, the temperature gradient that we're seeing between Mars and Jupiter locally within the asteroid belt, and it was seen as evidence that the asteroids formed locally to where they are today. And of course, that picture has changed a lot over time. Part of it was just that we were looking at a small subsample of the asteroids, and a lot of it's just, of course, a lot's changed over the past 3 decades.
Excuse me?
Yeah.
You've got a big peak for E, but E wasn't one of the ones in your taxonomy. Have they been changed into something else?
Yeah, that's a great question. So E, M, and P are not in my taxonomy. It's actually the X class. These 3 are separated by albedo only. Spectrally, they all look the same, but E is high albedo, M is mid albedo, and P is very low, so about 5% or lower. And so it's a big peak. Actually, this is the Hungaria region. So as you're looking at this as a percentage of asteroids, most of the asteroids in the Hungaria region are E-type, have a very high albedo. But in terms of, this is a little misleading because this doesn't take into account the number or the mass. So even though it's 60% of or 70% of the asteroids in this region probably represents 0.1% of all the asteroids in the main belt. So it's actually a tiny fraction proportionally to everything that's in there. Any other questions? So I'm fast forwarding to, I guess, 2008 to 2011. We've had the advantage over the past decade of some really large surveys that have given us an enormous amount of data for asteroids. And these surveys were actually not designed to observe asteroids, but because asteroids tend to pass in the field of whatever astrophysics mission is going, we get lucky and we get to pull that data and use it for ourselves. So SDSS, the Sloan Digital Sky Survey, and WISE over here. So SDSS was a visible wavelength survey over 5 different colors, 5 different bands. And then WISE was in the thermal wavelength, so we can derive albedos from the thermal data. And so what you can see here are maps of the asteroid belt. And so what you're looking at is distance from the sun, AU, in terms of orbit, and then inclination on these scales. So you can see this is visible wavelength spectra. You can see brighter asteroids, or what we're calling the S-type asteroids in this region, and then the darker ones are more C-type at the outer part of the belt. You see inner, middle, and outer there. And then same thing in the work of Messiro et al. You can see the bright asteroids here, and it tends to get darker as you move further away. And so,
The first one says color. Is that really color? Are we looking at the difference between orange asteroids and blue asteroids, or is it just albedo?
So these are albedo, and these are color in the sense of they're generally looking at the G minus R and then the R minus Z in terms of visible wavelength band. So you're comparing two different colors.
Yes, but what are the colors on your diagram?
Oh, so they transform these into basically just different spaces within the plot. So they say if you have a low slope in one part of the diagram, you're given this color. If you have a flat or negative slope, you're given this color. So it's just pulling the slope information and putting it into a color diagram so that you can see the differences. Sorry, I actually do have, I didn't put it in this talk, but I do have a plot that shows you how they change the colors as a function of how they change the colors of the dots as a function of the color of the asteroids in terms of that visible wavelength data.
Again, are the outer belt asteroids bluer than the inner belt asteroids?
Yes, they are. The spectral reflectance is bluer.
They're darker.
Yes, they're both bluer and darker. So the slope of the spectrum is neutral to negative, or very low, whereas the slopes of the brighter ones is higher. The albedo is higher, and the albedo is lower. So it's both darker and bluer, or brighter and redder. So both cases are true. And so we have these great maps of what the asteroid belt looks like in terms of composition, albedo, and the different trends that we can see. But one of the problems with these maps is that the data is very biased. What you're looking at is a concentration of asteroids that are brighter and closer to the sun, brighter in terms of they have very high albedos, and they're brighter just from a luminosity perspective just because they're closer to the sun, and you have the R squared factor in terms of how bright the surface is. Actually, R to the fourth, because it has to go to and back, because you're looking at the reflectance.
And there's a range of inclinations
Yes.
in all the groups.
Yes, absolutely. So you're also looking at a range of inclinations. So there's a lot of different biases in here. And so one of the things that I'm trying to correct is simply the distance and albedo, doing a simple correction for that. To correct for inclination would be a little bit more tricky, so I tend to ignore that in the work that I've done. But at least taking away some of the major biases is helpful. So I'll show the quick plot here, the importance of bias correction. So if you take the SDSS data, so this is SDSS right here, this is the visible wavelength color information. So I take this data set and I work on debiasing it. And so what you see here is the biased sample, where I take all of the data. The red is S-type, the blue is C-type. And so if I bias correct, this is what you see. It's a completely different story. And so the reason is these have like a 25 to 30% albedo, and these have a 5 to 10% albedo. And so there's just, once you correct for the fact that here you're actually counting a lot of, for example, 2-kilometer asteroids that are really bright and close to the sun, here, when you look at it this way, you're missing a lot of these bodies at the smaller sizes just because they're too dim for the survey to detect. And then the other thing you can see, so this is the V-types here. You can see it's a large fraction of the inner belt, about 15% or so of the inner belt. This is all part of the Vesta family, so fragments of the large asteroid Vesta. And when you bias correct for that, these have about a 35% average albedo, so they're very, very bright. So once you do the bias correction for that, they essentially disappear. And so what I'm doing is I'm removing the part of the sample that's biased. So most of these bodies are, like I said, about 2 kilometers, 1 or 2 kilometers across. But if you put a C-type asteroid rather than a V-type, so something that's 5% albedo rather than 35%, you can't detect it anymore. So if I couldn't detect it in one class, but I could detect it in another, I removed it from the sample. And so that's how you get this.
How do you explain that very sharp drop between, I guess it's between the inner and the middle on the first slide?
Oh, right here?
Yes.
Yeah, this is due to the resonance. So
Oh.
there's a section about right here where you have one of the major resonances that separates the different parts of the belt. And so the material in here versus in here is actually completely independent from the other. They're completely blocked off. The bodies of this size can't cross from one side to the other. And so yeah, this sharp edge really just means that there's nothing here. There's nothing there in that region, so that's why it looks kind of funny right there. And so this is what you get actually when you take the bias-corrected version of the entire main asteroid belt using SDSS. So we have a sample of something like 30,000 asteroids that go into making this plot, so a lot more than the 1,000 that they were using in the 1980s. And so it's a pretty messy plot. There's a lot going on here, and really what I say is the biggest takeaway is that the asteroid belt is a lot more complex than the picture that we had a couple decades ago when we were first starting looking at the asteroid belt in terms of its perspective. Another thing you can notice is that there's a lot of different colors here. Each color represents a different asteroid class. And so I'm calling this a compositional medley. You essentially find every single class of asteroid within the main asteroid belt, but then once you look into the Hildas and Trojans, you only see 3 different classes, the C's, the P's, and the D's. And so these are those carbon-rich, organic-rich classes that we expect would have formed further away from the sun. And so it's a really stark difference. It's not a huge difference in distance between 3 and 4 or 5 AU, but compositionally, it's really dramatic between what we see here and out here. I always like to show this plot because, so what I'm showing you here is mass on this side and semi-major axis. So one of the other main differences between the work in the previous SDSS work and the previous WISE work is that they were looking at everything in terms of number rather than in mass. So they were equally weighting a 5-kilometer asteroid with, for example, Ceres, which is 1,000 kilometers across. And so you give each one equal weighting, and from a mass perspective, they're obviously vastly, vastly different. And so what I wanted to do here was look at everything in terms of mass so that we could correct for the fact that some bodies are obviously very small and some are much larger, and have a clearer view of proportionally how much material you have of each class looking that way. So if I cut here, this is actually the limit of what we saw in the 1980s. And so here, the red is the S class. So really what we're doing is we're just recreating the plot from the 1980s, and it's obviously comforting to know that what they observed a few decades ago matches what we see today. Of course, the 1,000 largest asteroids haven't changed since that time, so we should obviously get the same results. So you have S, the blue is the C types, and then you move to P in the black, and then the purple is the D types. And so we see the exact same gradient. Of course, as you mentioned, the E types don't even show up because they're so far down on the mass plot. So this is what I was saying, is the mass of the Hungarias is orders of magnitude less than the rest of the main belt. And you can actually really see that clearly here when you're looking at it in terms of mass. And so this pink line here are your E-types.
Francesca?
Yeah.
So for objects that are smaller than some primordial size, and we can guess maybe what the primordial size is, then you're looking at fragments. And so what if you take away all the fragments and you say, I just want to recreate the asteroid belt out of things that would have been there and haven't collisionally evolved since then?
Yeah, that's a great question. So the primordial size, where they say it probably hasn't, if it's about 100 to 200 kilometers across, it's probably lived the entire age of the solar system without breaking apart. Whereas if you're looking at something here that's 10 or 20 or 50 kilometers across, it's probably a fragment of something that was larger previously. And so we can do that. Actually, that's really what I do next, is we break it apart by size, so you can see the different distributions of classes according to size. Although what I like a lot about mass is that you're actually, I kind of call it putting Humpty Dumpty back together again, is because just because it's a fragment doesn't mean it doesn't still tell you about the amount of mass of that composition that existed when the solar system formed. So you're kind of summing all of the masses together, even though they're fragments. Once you combine them all together, you're getting the whole picture of what originally existed. Whereas if you do it by number, then you're really biasing yourself towards what's fragmenting in any kind of collisional cascade. Does that answer your question?
Yeah, I guess I'm really wondering whether there's a different size distribution, which I think you're getting.
Yeah, exactly. So that's my next point. Is obviously this plot's pretty messy. There's a lot going on there. So what you really want to do is break it down by size, so you can look at the details of each one. And so this is something that's never been done before until this work. And I think it's actually really exciting to be able to see this view. It's really hard to find a good way to plot this in a way that you can see it all in one. So I think the pies are really helpful to digest quickly and easily. But you probably need a lot of different plots to look at all the different size distributions of each class to really dig into the details. So it's, in some ways the pies might be misleading, in some ways I think they're really helpful to know what's going on. So what you can see here is I've broken everything up into zones of the main belt and beyond. The reason is that each one is essentially dynamically distinct, at least in the size range of the asteroids that we're looking at. So essentially, since whatever the last migration period was, all of the material within each zone should have been locked in place. So, you really shouldn't see there's no reason that material would bleed from one region to the other. And then the second thing we do here is separate the pies by size. So here you're looking at the 100 plus size range. Here it's 50 to 100, 20 to 50, and then 50 to 20. And so you really kind of get this neat view of the whole belt. You can obviously see as you move over, so this is again the largest asteroid, you can see it going, well, of course, by mass. Vesta takes up most of the mass of the inner belt. So even though by numbers, S dominates, by mass, the asteroid itself for Vesta dominates here. So you can see S to C to C to P, and then out to D as you move further away. So the same exact trend we're seeing. But what's really interesting is as you move down in size, you do see differences. So I think what's fascinating here is if you look, this is about a quarter of the C-types are about a quarter here and a little bit less than half there. But we see it in both zones. So there's just a lot of little things that we can look at. Here you can see that as you move down in size, you're seeing differences. So here D-types dominate D-types, and then you have a large fraction of P-types as you get down to smaller sizes.
Is there a relationship between the composition and the breaking strength of the asteroid? So
Probably.
Is there an effect here that certain types of asteroids are going to be more existing in fragments?
Yeah, I think the answer is yes. So surprisingly, but figuring out which ones would last longer is not always as easy as you would think. So originally we had thought that the C-type asteroids would be less strong than the S-types. So the carbon-rich ones tend to be sort of light and fluffy, have more macroporosity. But what we found when there was an asteroid flyby probably 10 or 15 years ago of Mathilde, I actually showed it earlier when you saw some of the flyby asteroids, we found that there were these huge craters in this C-type asteroid. And so what happens is essentially it looks like when it gets hit, the material just gets compacted rather than breaking apart. So it's actually hard to know based on the material and the porosities what asteroid would break up faster or more easily than another, just because of the dynamic between lower gravity, macroporosity, and composition. And even electrostatic forces and things like that come into play when you're in such a low gravity regime. So we have, does that answer your question? Yes. Okay. Any more questions? Yeah.
I do have one.
Oh.
What does the size of each circle represent? That is the area of the circle. Is that the number or is that the mass?
This is the mass.
Thank you.
Yeah, thanks. So this is, each of these pies represent a certain amount of mass, and the mass is actually listed here. Sorry, I didn't explain that earlier. So this pie here represents 10 to the 20 kilograms. This pie here is 4 times 10 to the 18th kilograms.
So that there's a bit more mass in the larger ones, but there's a lot of mass in the other size groups.
Yeah, exactly. So definitely the mass of the largest ones dominate. There's a significant amount of mass in the smaller sizes, but you can see factor of 10 difference.
Is migrations insignificant at smearing this out?
That's a good question. I think the answer to migration is somewhat in here. I'm actually going to talk a little bit about that next, what we see evidence for migration within here.
So, just quickly, you must have had to make an assumption about the densities of these objects when you're
Yes,
doing the math.
absolutely.
How much uncertainty does that introduce?
A lot. A lot. So there's a lot of uncertainty in the densities. Basically what I do is, there's a lot of assumptions that have to go into making this kind of a plot. So we have to assume an albedo, which means we know the average albedo for each taxonomic class. So we assume an average albedo for each class and use that to calculate size, diameter. We assume a density, which again is using the average density per taxonomic class. Our values for albedo are much better defined than for density. Density is a much harder value to measure. So there's a lot more uncertainty in the density, but if you calculate mass, it's IR cubed versus density, which is not. So even though the uncertainty of the density is large, I think it's really the radius that any uncertainty of the radius would make a much greater impact on the masses.
You may be about to talk about mixing, in which case I won't ask any question.
I am going to go into that a little, so maybe I should. Yeah, let me go into that a little because it sounds like some of the questions will come there next. So we created this nice big map of the asteroid belt, and the next question is really, what does it mean? And what does it tell us? And so there's so many questions that we can ask. I'm calling this like, what's next? The Asteroids 4 perspective. Asteroids 4 is the book that just came out in the Space Science series. They come out about every decade, every 10 to 12 years. And so this one just came out in December. And there's a lot of different questions that we want to ask related to where asteroids formed, how they evolved, both physically and dynamically. And so some of the details of those questions I've put out here. I'm going to go through a couple of them and talk about what we see in the asteroid belt in terms of the compositional map we've built and any follow-up data we've needed to take to confirm any of the things that we've seen. So one of the first ones, and this has a lot to do with migration, is what are the distributions of S and C, so S-types and C-types mean? Again, S and C is silicate-rich versus carbon-rich. And so what we see is S-types dominate in the inner part of the belt and C-types dominate in the outer part of the belt, but we definitely see a lot of overlap and mixing between the two classes. Even though we had originally started with the hypothesis that everything formed in place in the main belt, it's really hard to explain how so many different asteroids of different compositions could form in such a narrow range, such a narrow distance from the sun. It's really 1.5 AU across. So the favored explanation is that these formed in different populations. So for example, the S-types formed closer to the sun, again in a warmer environment where you get your ordinary chondrite-like bodies. And then the C-types likely formed further away, they're more carbon-rich. So in this case, you're looking at Jupiter and Saturn, so might have formed outside of the giant planets. And the scenario, so one of the scenarios that they've been looking at recently is called the Grand Tack scenario, where Jupiter migrates inward. So you have these two populations. Jupiter migrates inward, as we see for giant planets in many extrasolar systems. And it scatters the S-types backward, and then there's actually a period where they tack because Saturn gains mass as it moves forward and follows Jupiter. It hits a critical mass where it actually tacks, and they move back in the opposite direction. And so when it moves backward, it scatters these bodies and the C-types back into the asteroid belt that we see today. And so there have been models to look at this scenario that work pretty well, but of course they work qualitatively, not quite at the level of detail that we see in the asteroid belt today. So what's the solution for this compositional gradient? The first one was originally thought that it was primordial. In fact, it is probably primordial. It does tell you about the temperature and compositional gradient in the disk, but not necessarily just between Mars and Jupiter. It's more likely that you're looking at a gradient from, say, 0.5 AU all the way out to tens of AU. So you're really looking at the temperature gradient across the entire solar system, not just the main asteroid belt. And as we're seeing the more favored explanations now with a few different migration scenarios, is that it's more likely that we're looking at the asteroid belt as a melting pot from all bodies that formed across the entire solar system and then were scattered in during migration periods. So I'll just show This is the migration scenario by Kevin Walsh called the Grand Tack. And what you see here is the scenario that I described to you where Jupiter and Saturn move inward. It scatters the S-type bodies, the red ones here, outward. And then, here, I'll run that one more time. And you can't see the blue population here. It'll be in the next video. So this is the inward migration. This is an outline of where today's asteroid belt is located, eccentricity and inclination on the two plots. So you can see the material started inward, migrated, and then got scattered out. And then this is the second half, where Jupiter scatters out, or migrates out, scatters bodies inward, and you end up with material everywhere, but really the only location that's stable over billions of years is right here. All these other regions are unstable, so interactions with Jupiter and other giant planets remove those bodies over time. I'll run this once more. So again, you end up with this mix of S and C in here. And of course, there's a lot of different asteroid classes. The modeling is fairly simple, just looking at two different populations in two different locations. Then the second part would be how do we form the Hilda and Trojan regions that had those darker, more organic rich material, and that's expected to happen in the Nice model, which material from the Kuiper belt was brought inward into the inner solar system. So this is one of the other questions related to the SNC, and this is something that I mentioned a little bit earlier, is how we see a difference in the C to S ratio as you go down in size. And I'm not sure exactly what this means. I think we've just found the trend and we need to sort of look into this. It's certainly not a bias, because as you're getting more C-types as you go down in size, the C-types are darker. So there's actually a bias against discovering these. So the fact that we find more is surprising and clearly not a bias. So some of the solutions are that the size frequency distribution of families changes at smaller sizes. So that could mean, so asteroid families, you start with one parent body, a large body collides, it breaks into a lot of fragments, and the fragments are called the family, an asteroid family. So it could mean that when a family forms, different compositions break apart into different sizes. It could mean that as the collisions happen over time, as you were mentioning earlier, some compositions break down or break apart easier than others, and so you're seeing maybe here the C types are surviving longer than the S types because they're more populous here than here. Another interesting scenario that's been proposed is shocked S types. So if you take one of these bright, ordinary chondrite-like asteroids and shock it with an impact, it significantly darkens the surface and masks the bands. And so you end up with a spectrum and albedo that looks like a carbonaceous chondrite. And so you from space, you really can't tell whether it's an S or a C. There's a lot of new lab work looking into this. I think it does happen, but it's probably not a significant fraction of the population. But I do think it's a part of the story. Here's another question. So why do the Trojans and Hildas change with size? So this is another thing I mentioned. If you looked in the outer part of the solar system, as you look down in size, you're seeing changes. This was actually also seen by Tommy Grave and the WISE data. So they're looking at the solid line is D types, and the dotted lines are C and P types. And so you can see as you go down in size, so this is diameter, so I guess you go down in size this way, you see them flip. In both the Trojans and the Hildas, you see the same trend, which is really fascinating. So why does one become more prevalent as you go down in size? So there's a couple scenarios of why this might happen. It could be an age-related weathering process. So over time, the asteroid surfaces are subject to space weathering. They get bombarded over 4 billion years by high-energy particles, and so that can cause chemical changes on the surface. It's something we see and have confirmed on the S-type asteroids. For example, with the sample return mission, the Hayabusa mission to Itokawa, we actually did confirm the space weathering processes on those bodies. We just started lab experiments on these types of compositions, so it's possible that it's weathering related processes, but we're really not sure. This is a pretty new trend. There could be real compositional differences. So for example, as you move down in size, are the compositions of the smaller bodies different than the larger bodies in the Hilden and Trojan population? And then I sort of just have a wild card. Are there other dynamical or other physical properties that we're not taking into account when we're looking at the different size ranges? Are there D-types in the inner main belt? So this plot that I showed earlier, I just removed everything but the C, P, and D types. So the D types are here, this little blue line, and they exist throughout the entire main belt out to the Hildas and Trojans, even though they're dominant here. And it was actually a surprise to find them in this region. Dynamical models that have been run that showed D and P types being transferred from the Kuiper belt out here all the way into the main belt showed that they only could reach here when you transplanted them inward. So they could only reach the mid belt. And so, and at the time, our observations had confirmed that. If you looked at the larger bodies, you could see that the black ones are real bodies and the red ones are the simulation. And so we could see that they stopped here, and then here the green is just asteroids in general of any type. So you could see they didn't exist beforehand. So it was a surprise when SDSS found more of them, and so I did a follow-up survey of these D types and actually did confirm them. And so this is additional work where we confirmed that they did exist there. And so finding them in the inner part of the main belt was surprising, and basically what that says is there's more constraints for the dynamicists to use to figure out how to transplant that material further inward. And so I know that they've been working on revising the models. There's also, you could also say they're not related to the outer solar system material. There's a lot of degeneracy in the spectrum. Just because we see a flat red spectrum doesn't necessarily mean that they're all the same. So that's another possibility, that these bodies are not compositionally related to the ones further out. And then this is the final one that I wanted to talk about, is where is the missing mantle material? So this has been a big question over the decades, is we've expected that the largest asteroids must differentiate, and a simple model for differentiation we've looked at over time has been just a metallic core, an olivine-rich mantle, and a pyroxene-rich crust. Anyone who's a geologist is probably grimacing at how simple this model is. But spectrally, they're easy to distinguish. The metal core will look like an X-type, a very flat, featureless red spectrum. The olivine has this clear feature, and the pyroxene looks like a V-type, like this. And so we don't see a lot of, we would expect that if asteroids differentiated and broke apart, we'd see a lot of olivine in the main belt, but we don't. And so some of the answers to this question have been maybe they differentiate differently than we expected. Maybe they just don't form these olivine-rich mantles. Wendy Constantin has done a fair amount of work in that. Perhaps that these bodies formed elsewhere, that they didn't form in the main belt. In fact, it's likely that they formed in the terrestrial planet region, and then the fragments were later delivered to the main belt today. So the material isn't missing because it was never in the main belt in the first place. It was just scattered out there. The third scenario was called the battered to bits scenario, where they thought that, well, we're looking at the largest asteroids, we're not finding enough mantle material. Maybe if we look smaller down at smaller sizes, maybe the fragments are just below our detection limits. And this is probably not favored right now because we've been able to go further down in size and we're still not seeing the material. So what I've tried to do is search for mantle material, see how much there is in the main belt, and see how it's distributed. So A types are distinct. A types are the olivine-rich material, so these are what we expect the mantles to look like if they were out there. Again, it's so different from all of the other asteroid types that it's very easy to distinguish them. We used SDSS to search. I call this tool a good tool for finding a needle in a haystack. A types are extremely rare. In the sample of 100,000 SDSS asteroids that were observed, we probably only had a few hundred in our sample that were worth following up. And so we targeted this region. So here you're looking at the asteroid slope, and then what we call the 1 micron band. So the Z to I, whether it looks like it's going down with an olivine or pyroxene feature, or it would be positive if it's a straight slope here. So we just use this to kind of break apart the different taxonomies, identify where A types would be, and we want to follow those up.
What is the orange rectangle?
So this is where the A types exist on this plot. So this is a question you were asking me earlier, is how do you tell the different colors of the asteroids? And so you're looking at the Z to I and the GRI slope on this axis. So your C types have a low slope and a fairly flat Z to I, so they're around 0 for both. The D types have a very high slope, so you see them up here. V types have a moderate slope and a very deep Z to I, that's your 1 micron absorption feature, so they fall down here. And then your A types are up in this region. And so I've boxed off that region as the target zone for the follow-up observations. And so this is where the actual individual bodies that we targeted were located in this SDSS classification space. And so you might ask, why do we have to even follow up these observations at all? And the reason is because there's degeneracy in the visible wavelength. So if you look at just the visible here, you can see a lot of these asteroid spectra line up very nicely, but once you take near-infrared observations, you can see a huge difference in the bands right here. So your big, broad, deep bands here, this indicates essentially pure olivine, whereas you can see the band center out here, the band center here is closer to 0.9, whereas if you're looking at these red spectra here, this is a more S-type or ordinary chondrite-like spectrum that's a mix of olivine and pyroxene in the reflectance spectrum. So that's why it's really critical to do follow-up observations, because you could find something that in the visible looks like an A-type, but once you actually look and can see the real composition, it might not be.
And there's no way space weathering can convert your typical A-type to one of these, the red and non-A-type.
So, yeah, so the space weathering actually reddens a spectrum, so you can see that these ones, because olivine itself is flat, so you see this big band and then it would go flat. These are likely very space weathered or also have a mix of metal, which is causing them to redden so much. But yeah, space weathering wouldn't change your band, and that's the most important part to distinguishing the composition. Definitely band centers. So you can't change your band center with the space weathering. So these were the SDSS predictions. So these red dots are the 5 colors from the SDSS data, and in the gray I've just noted the average spectrum of an A-type asteroid so that you can really see that these fit the trend very well. So they're a perfectly classed asteroid in terms of an A-type. And then we followed them up on the IRTF, a 3-meter telescope in Hawaii. And here's visible wavelength, here's near infrared, and so now you're looking at the deep 1 micron olivine feature. So we've confirmed them, which was really exciting. Here's the results of the survey. We took 60 candidates that we observed, and only 19 of them were actually A-types. The rest of them ended up being S or some other class. So it was really only a 1/3 confirmation rate. Like I said, a lot of this has to do with the degeneracy of the visible wavelength region, which is why we really needed the follow-up data to be sure when we were looking at them.
Could that same degeneracy be true in all the other classes? So should we expect that maybe 60% of the time the
Yeah.
classification is wrong?
Good question. No, I don't think so. The A-types are really a rare, separate case. Because they're so rare, you're more likely to end up with contamination of the more populous classes. So S, you're something like 90% likely to get an S or a C, and those are very distinct in the visible wavelength, so they're easy to tell apart. But once you get into something that's more rare, in general, so for example, the V-type asteroids with the deep 1 micron feature, even though those are also an extreme class, very different spectrally from the other classes, in the visible, it's very distinct. And so Nick Moskowitz, who's actually a postdoc here, did a similar follow-up survey for V-type asteroids, and his confirmation rate was something like a 90% success rate, whereas I'm getting a 30% success rate. So it depends on the class, and this just happens to be a particular case where the visible wavelength is not a good indicator. So this is the previously known A-types distributed in semi major axis and inclination space. And these are the ones that we've discovered from the follow-up. So what was pretty exciting about this work is we see them really evenly distributed throughout the entire main belt, even out into the Sibylles at 3.4 AU, which is really pretty far. You even don't find many S-types in this region. And you don't see a concentration anywhere, which is really surprising. I think if you would ask someone before this follow-up survey, people would say, oh, they probably concentrate in the inner main belt. But we really find them everywhere.
What are the green?
So the green are the ones that we had already known before my survey. We had already.
What are the grays then?
The gray is just the background. So this just gives you a sense of where the main belt is located in semi-major axis and inclination space, just to make you see how these bodies are distributed with respect to the rest of the main belt. And so what we can do is we can use, because we know how complete SDSS the survey was, so in some cases it would say 50% complete, some size ranges and locations it was 50, 30, 20% complete. What we can do is we can say we found 10 A-types in this region of the belt and it was 50% complete and we had a 30% success rate. We can use all those numbers to calculate how many total A-types statistically we expect to find in the main belt in general. And so that's what I did next, is rather than just saying we have 19 confirmed candidates, I can use that to say how many total pieces of mantle material do we actually find out in the main belt. And so I won't go through the numbers really here, but the number in the MPC is the total number of asteroids in the size range I'm looking at. So H magnitude is a proxy for size. So 11 to 16 we're looking at. 16 corresponds to about 5 kilometers in size. So there's 400,000 total asteroids in the main belt above that size range, and there's only 565 of them that are A-type. And then I can calculate masses here. You can see it's 10 to the 16 and 10 to the 15 at each size range, whereas when you were looking at the plot of all of the asteroids, we were looking at 10 to the 20th and 10 to the 21st among the largest sizes. So they really don't represent a lot of material in the main belt. I'll skip that. So just to kind of conclude what we found from the A-type project, so we confirmed that A-types represent a very small fraction of the total number of the main belt asteroids. Previously, as I had said, they said, oh, well, if you look at smaller sizes, maybe they're there. Maybe they had just broken up into smaller and smaller fragments. We've looked down to 3 to 5 kilometers, and they're just not there. So that's not the solution. So there's no significant undiscovered olivine-rich material. A-types are distributed throughout the entire main belt, and a significant fraction of the total A-type mass is in the largest few. So you could actually see more mass in the largest bodies and actually very few fragments, even relative to what we see among the rest of the classes, very few are A-type. So there's a concentration of mass in the largest bodies. And so this actually really makes us lean toward having things that formed in the terrestrial region and scattered out into the main belt later on, which I think in terms of how they formed makes a lot of sense, and why we see them distributed, so few of them distributed, but distributed everywhere in the main belt. I think the two pieces of the equation are starting to come together. Yeah?
So if you see an asteroid that doesn't have a 2-micron absorption feature, you would call that an A-type, correct?
It has to have the 1 micron feature. That's really what distinguishes it.
So I guess what I'm getting at is how much pyrexene would you have to mix it into an olivine-rich asteroid to where it wouldn't become A-type spectrally anymore. So you have something 90% olivine, 10% pyrexene.
There isn't a hard number, but it's somewhere between 80 and 90%. Yeah. And so you'll be able to see it visually in the spectrum where the band center shifts, and the width and depth of the band changes. But yeah, the A-type boundary is loosely between 80 and 90% olivine to pyroxene ratio. Yeah.
So you mentioned that the majority of mass is in the large asteroid in A-type. Does that mean that the asteroid experienced a big impact in the past and absorbed of the mantle materials, and the small materials became small pieces later on? Is that
Yeah, it's a good question. This is a really new result, and I don't think we have an answer to why. We actually just discovered this very recently, that the A-types are more heavily weighted to the larger bodies than any of the other classes, so that the size frequency distribution is shallower than all the others. So we don't have a reason yet. One of the proposed explanations that I think is really interesting, I mean, obviously it means that collisionally, the few A-types that exist haven't had any major collisions that have caused them to break down into smaller sizes. I think that's fine within the scenario because there's only a few of them, and they've survived, and I think that's fine. One of the interesting scenarios that's being put forth is that because we see them at the large sizes, and because the mass fraction between the V and A, so your pyroxene to olivine ratio, which is essentially your crust to mantle ratio, is very high. You have a lot more mantle than crust. They're using that as an argument that that these A-types might not have come from small planetesimals that formed in the inner solar system, but might have actually come from large planet-sized bodies. So a Mars-sized body, for example, or just some large protoplanet in the inner solar system, because that's the only way you could end up with that much olivine compared to basalt. So that's one of the interesting theories that's being put forth, not published yet, but something that we're looking at to explain that difference.
So Francesca, why would the A-types avoid collisions, unlike all the other asteroids?
It's just about the numbers. So because there's 1,000 large asteroids, and however many they were originally, there's just a probability of certain ones, of a certain number being broken up into smaller sizes. So I think because there's so few, there's only a handful of the largest ones, the probability that those 3 or 4 didn't get catastrophically broken up is fine in terms of the total number of asteroids that are large and that were broken over time. So, yeah.
Do these odd pairs of asteroids that you see, if you look at the two of them, do they tell you anything about if they're formed in wildly different regions? That tells you something about the capture probability?
Oh, the asteroid pairs?
Yes.
The asteroid pairs, I believe, are assumed to have come from the same original body, because if you track their orbits back in time, so the asteroid pairs, they're bodies that have almost the exact same orbit but are in different places along the orbit, and so what they do is they do backward integrations on the orbit, and they find that the bodies actually originated from the same parent at some point in the past, and so those are actually expected to form from the same body. I don't know if you're also talking about binary asteroids, so if you have 2 binary asteroids orbiting each other, there's a number of different formation scenarios, and I think capture is one of the more rare ones. There are a few cases where we expect capture, but a lot of the reasons that we form binaries is when you have a body. I think one of the most dominant reasons is you have one asteroid that spins up, especially at the smaller sizes, spins up fast due to radiation from the sun. It's called Yarkovsky effect. It's a radiation effect that causes a torque on the asteroid, speeds it up, and eventually it hits a spin limit where it's moving so fast that the internal strength of the body can't hold it together anymore and actually breaks it into multiple pieces. And so most of the reasons we see pairs or binaries of asteroids, it's originating from the same body, not from a capture scenario. So I didn't even actually go through my conclusions, but the last thing I was just going to say is just wrap up what I had gone through in the talk. Our original paradigm was that the formation of the solar system and the evolution since was fairly static, that the asteroids formed where they are today. New trends and a lot more data show that there's a lot of diversity of asteroids and new trends at the distribution across distance from the sun, but we're also seeing more mixing of asteroid types at the smaller sizes and different trends at the smaller ones than we do see at the larger ones. And so really the next step is follow-up. There's a lot of questions that this map of the asteroid belt brings up that we don't have answers to yet. And so it involves follow-up work in terms of follow-up observations to confirm the data and to dig into more detail of the trends. And then also for the dynamicists to look and start tweaking their models and making sure their models are consistent with the details that we see in the asteroid belt today. So, thanks.
Okay, we have time for a few questions. Larry?
So the discussion of olivine and pyroxene is based on the 1 and 2 micron bands.
Yeah.
Those require the olivine and pyroxene to have iron in them because it's an iron transition. So pure ensitite and forsterite don't show those features.
Yes.
So is it possible for asteroids formerly known as E that are featureless could be, say, forest-type or Insta-type mantles of reduced planets that broke up?
Yeah, that's a good question. So the E-types are generally considered to be either Insta-type chondrites or Insta-type achondrites. That's generally the mapping that we make between the asteroids and meteorites. I don't know how good it is. They match with an albedo and a spectrum because they have very high albedos. So I don't know. Generally when we're trying to find the complete picture of a differentiated asteroid, you're looking at the X-types or the M-types that have a medium albedo and are expected to be very metal rich, and you're looking for a core.
Right. But you're saying you're missing the mantles of those. So if those were really reduced bodies to begin with, got broken up,
you're saying
the mantle might have been an Insta-type achondrite, and that might be what you're looking at. So
yeah,
is there...
that's possible. There's probably fewer E-types than there are A-types.
Oh, okay.
Yeah. So you're not going to find those in the main belt. There's probably, I think I can think of 3 large ones that exist in the main belt. The reason you think there's so many is because of that Hungaria region, and it's actually an asteroid family.
Well, it's not even that so many, but I guess it's also that, the spectra don't tell you that much. So
yes.
If you had a space-weathered Insta-type achondrite, could
yeah.
that darken it so it looked like an M or whatever? I mean...
Yeah, that's a good question. So there could be there definitely could be a connection there, and I think people have it's hard to follow that path because, one, there's so few of those candidates out there, and it's also just hard when you're looking at a featureless spectrum. There's just so much uncertainty. It's like you have really no idea what's on there. Whereas we kind of tend to hang on to the absorption features because that's really concrete once you can identify that absorption.
So if you redid your mass plot that was in terms of asteroid type, and you redid it instead as a undifferentiated and then core, mantle, and crust, how would the masses turn out?
Yeah, so that's a good question. So if you did differentiated versus undifferentiated, I mean, it depends on your different definition. So we tend to think of carbonaceous chondrites as completely undifferentiated. We tend to think of the S-types, the ordinary chondrite-like ones, as experiencing partial heating and melting, but not obviously complete differentiation.
Right, so I
you
still
would
count those as undifferentiated.
Okay, so then you'd completely take those away, and those are like 90% of all of the asteroid belt at least, and then plus all the other smaller types. So you're really just looking at...
So 10% of the mass would be undifferentiated, but you're still missing...
Yeah, not even. I'd say maybe 1%.
Okay.
I
And
guess
then
it
you're
depends
still
on if you count
missing
Vesta
the
or not.
mantle and...
So Vesta is 1% of the main belt, or a couple percent of the main belt.
And then even within that, you're still got the wrong mass balance for core, mantle, and crust.
Yeah, so if you remove Vesta, and you just look at the middle and outer belts, the basalt ratio to the A-type ratio do not match. We tend to not look at the metal, the X-types, just because, again, there's so much uncertainty. I think we can do a back-of-the-envelope calculation if you say there's this many X-types with this albedo, and the conformation rate. You really have to follow those up with radar albedos, radar measurements to know if they're metal rich. That's really the only way to be sure. Sure is sure astronomically. And so we can get a general estimate of how much metal there is. I think that's the most uncertain. So that's why we're focusing on the basalt versus albumin ratios.
John?
I think you have to be careful attributing too much to solar condensation temperatures in the nebula, because if you look at the carbonaceous chondrites, they're mostly depleted in moderately volatile elements like lead and potassium and so on. So if they're supposed to come from 5 or 10 AU, as the Grand Tack model would suggest, the temperatures are far too cold there to explain that kind of depletion. So something else has to be going on too.
Yeah, the C-types are really a mystery. Just because it's without features, it's really hard to know what's going on. I think the S-type story we've really nailed down, and how they're related to ordinary chondrites. The features help a lot. When you're looking at C-types, I'll give the example of one new paper that's out by Pierre Vernazza that actually suggests that carbonaceous chondrites and the C-types are not related. In fact, the best samples on Earth that match are IDPs. And so maybe the bulk of the C-type material really doesn't match the carbonaceous chondrites. They're a sample of CMs that match some of the C-types, and that you can look at the 3 micron hydration feature to make that link. But otherwise, you're just matching featureless meteorite spectra to featureless asteroid spectra. And so the question of how many of the actual, I guess I make an oversimplification when I say, oh, C is carbonaceous chondrite. I think in reality, that's not the case. There's a subset of carbonaceous chondrites that match a subset of the C-type asteroids. I'm not sure we have samples of all of the C-type asteroids in our meteorite collection. It's harder to deliver them. It's harder for them to survive entry into the atmosphere. So I don't think we have a good sampling of what the C-type asteroids are made of. And that's part of the reason that we are motivated to do sample return missions of these primitive asteroids. OSIRIS-REx is doing it, and then Japan is sending Hayabusa 2 that should be also sampling a dark asteroid. So I think there's a lot more we need to understand there.
So is there another spectral class that could be the parent of the carbonaceous chondrites?
I think it's a subset of the C-types. But I think that it's the problem where I expect there's a really wide range of compositions within the C class, and we just can't tell from the measurements we're able to take from the ground. Because I think that's why we need a piece of it to know. So yes, I think that the carbonaceous chondrites are linked to a subset of the C types, but we don't know which C types. It's just a black bag that we're pulling pieces out of, and we can't really tell. At least not yet.
So I have a question. I was at a workshop in January, and for the first time ever, Morbidelli seemed to be backing off the Grand Tap a little bit. And John has questioned whether the Nice model happens. And there are some interesting new dynamical models. So how is that going to change your interpretation of what's going on in the asteroid belt if those prove to be incomplete or totally wrong?
No, I think that's a great question. And one of the tricky parts with the dynamical models is they're constantly being modified, but they're always based on the observations. So you can never prove a model because the model is based on the data. So you never say, oh, look at what we see, it's exactly the way the model is, we proved the model. It's just the opposite. They've used the data to make the model, so it ends up being the circular argument. It's funny, I did see Morby in January, and he didn't mention that. It would have been good to know.
If Morby,
All he said was,
if he disavows the Nice model, or is he
He
get
hasn't-
out of the city?
he hasn't disavowed either of them. What he said was, they are just models. So
Yeah, no, I think it's good that they do have a good sense of they're willing to let go of models that don't work. Hal Levison recently came out with a drastically different model. He's really shaking things up, where he actually, using modern, not what they did in the 80s, modern modeling, where he actually forms everything locally and forms the asteroid belt locally, with just accretion over time in that region. And so it's a really fascinating model that he can generally reproduce the asteroid belt and the planets in the correct sizes, including the small Mars, which is why the Grand Tech model was invented, for the small Mars. And so it's fascinating that he, in his preliminary model, was able to do that. So I think it's made everyone say, oh, well, that's really, really different from the migration scenarios we're looking at now and that are favored now. So in terms of the data, I think the data is there, and what the dynamicists do to interpret it will continue to change and evolve. So I like to show the models because I think it sort of illustrates where we are in terms of interpreting what we see for the data, but I am certainly interested in seeing how that changes over time.
Good question. One of the things I read in the past was that the Borealis Basin in Mars was created by a colossal collision. How different are these asteroids from the Martian crust that maybe could have resulted in some of
you mean the A-type asteroids?
Well, in general, the asteroids.
Asteroids in general. The composition of the asteroids in general, the S and the C types are obviously very different from the surface of Mars. They also undergo lots of collisions out there as well. If you're talking about specifically the A types, I actually don't know how we could distinguish whether one of these bodies could come from Mars. Actually, maybe some of the meteoritists out there have an idea. That's something that as we've been thinking, maybe some of these olivine-rich asteroids came from a protoplanet, an actual planet-sized body in the early solar system. Sort of makes us wonder how much could come from Mars, how much could come from planets, how much of this was actually really just small bodies that differentiated. So I don't have an answer to that, but there is a Mars Trojan that is A-type. Its spectrum is very distinct from the other A-types in the main belt. I've never seen a paper, but I've heard word of mouth saying, oh, well, maybe that could have originated from Mars. So, fun.
Well, Francesca will be around for the rest of the day. She'll be at lunch club, so if you have any burning questions, come and look her up today. So thank you once more.